So let's get started. Let's get into the details. So what I want to talk about today is basics of fiber channel. This topic was recommended to me by somebody who attended one of the boot camps, the CCIE boot camps, and they really thought that a lot of networking focused people, so Ethernet networking guys, iOS based engineers, they really benefit from this kind of explanation. Because what I want to do is I want to explain to you how fiber channel works in the basics. So what are the ports, what are the forwarding characteristics, what is the addressing used, and what kind of terminology is used for that. So I want to run you through the topic of fiber channel 101, meaning I will explain what I just said, the basics of fiber channel. But I want to share to you about that by using the knowledge that a normal Ethernet networking person should have or will have. So I want to run you through a number of things. So let me first introduce myself. So my name is Rick. My name is Rick Murr. I am the CCIE data center instructor here at IP Expert. I am teaching all of the data center related classes, like last weekend's UCS class, and we will be doing a number of CCIE data center boot camps in the coming 2 months. So if you want to join one of them, reach out to our salespeople. So this topic will of course be an overlap with that. I will do some of this lecture again in the CCIE data center boot camp, but then we spent a lot of time on this. So my name is Rick. You will see my email here on the slide. If you have any technical question, feel free to email me or reach out to me on Twitter. So any question that you might have regarding the CCIE data center program or regarding the CCIE data center lab test, let me know and we'll figure it out. We'll figure out a solution for your technical question. Again, something more about the classroom. On the right hand side, a lot of people already found the chat window. If you have a question, feel free to interrupt me. If you do not fully understand something I say, please interrupt me and ask your question in the chat window, and I'll be happy to respond to that. So you might be looking at that side a number of times, then I'm looking if there are any questions in the chat window. Right, so let's get started. Like I said, we're going to focus on fiber channel 101, and I want to run you through that by covering topics that are known to you by Ethernet networking people. So I want to run you through the OC layers of fiber channel. I want to run you through all the terminology, and I want to compare that to Ethernet. Then I want to talk a little bit about forwarding. So how does fiber channel forwarding work? So not only talking about the encapsulation of the header, but also for how does address resolution work? How do two nodes on the network find each other? So a lot of that technology, and how does the network converge, right? How does the network discover its topology? How does the switches know where to send traffic to? So the basic concepts of forwarding. I want to talk a little bit about access control. I will not go in depth about this. I will just touch the feature and what it will do for you. Because if I need to run you through all about access control, then we're here for another 3 or 4 hours. And I want to finish today with a short demo by just bringing what I just told you into a real life situation where we will start configuring a basic fiber channel network. I will bring up 2 hosts on the network. I will bring up a link between 2 switches, and we will verify some of the things that I told you by doing some show commands. And again, interrupt me if you have questions. No problem whatsoever. If you have any question, please interrupt me. So I want to get started to talking to you a little bit about storage on the first place. Why do we need fiber channel? Why do we need that whole new protocol stack and all new encapsulations and even new layer 1 signaling? Why do we need that? Well, at first, where is this placed? Where is my fiber channel network placed in the world? So first of all, we have a PC or server, and that PC or server wants to store its data somewhere. So in the past, and actually some current technologies revise that, we inserted hard disks in the PCs. So we inserted hard disks in the PCs, and there we could store our data. This is something we can call direct attached storage, or DAS. That means that the hard disk is physically connected with a short cable to the PC or server. A short cable, I mean just 3 feet, or a little bit longer, but just it's inside of the PC. So directly attached storage. That's where it began. Then the servers had too much data, and actually we want to share some of our corporate data maybe with multiple servers and multiple PCs. So we have multiple PCs and servers that want to have access to the same storage. That's not very scalable if we are using direct attached storage all the time, because now every time we need to copy files over and stuff. So they came up with that I can have a disk, and that disk, or the case where it's in, has an Ethernet port. And that Ethernet port talks things like CIFS or SMB, which is the Windows file sharing, or NFS, or AFP for Apple machines. So all kinds of networking protocols related to making a disk available for everybody. And not really a disk, just a folder. So a place to store and read files on the Ethernet network. This solution is called NAS. So a network attached storage device. So it's not a server. It can be a server with some disks running Windows Server and then publishing some of its folders. But it can be some dedicated equipment. It can be very professional, but I know a lot of you at home will have some of these devices to store all of your content. So we have direct attached storage and we have network attached storage. The place where the fiber channel framing comes into play is, in this case, this disk is connected to an Ethernet network, and that Ethernet network is shared with all other devices, and all kinds of other traffic is traveling across that network. So traffic for the disk, but also traffic between servers will flow across the same network. That is a network attached storage device. Where our fiber channel comes into play is in places for, let's say, the data center. So we have two servers that want to have access to some shared storage. They are connected to an Ethernet network with maybe a default router in there. And then we say, all right, we have so much traffic coming from this server, and we have also so much traffic going to the disks. We need a separate network for this. So we will start building a separate network where we attach all our disks, and this is something we call a storage attached network. So no longer the storage device is connected to the network. Now we created a specific storage network just to run storage traffic. This does not indicate that it runs fiber channel. I can perfectly run a SAN using Ethernet because it's technically just a separate network, a separate physical network to run the storage connections from servers or PCs going to disks. Now, so I say you can do this with both Ethernet, just what we're all used to, but I can also do that with another protocol, and that protocol is called fiber channel. The fiber channel protocol was designed during the time that Ethernet was still stuck at 10 meg or maybe 100 meg. And fiber channel already started at the 1 gig speeds. When Ethernet went to 1 gig speeds, the fiber channel standard easily updated its standards to 1, 2, and 4 gig. And after that we got 8 gig and also 16 gigabits a second fiber channel. The 16 gig is a very recent development, by the way. So we developed fiber channel for speed. And of course, traveling or transporting disk frames, so data blocks between the server and the disk, on the most efficient way that we can think of. So it has some optimizations because it only needs to transport one certain type of packet. That is a storage packet, where Ethernet can be used to transport anything. Fiber channel is used to transport storage stuff, nothing else. Although there is an exception, but that's a small one. So we developed fiber channel for speed. That's why we needed a separate network, because these links, this Ethernet link and this fiber channel link, do not share anything. Really nothing. They are both data communication protocols, but they share nothing. So all the concepts you know about Ethernet change on the world of fiber channel. Although, like I say, it's still data communication, and data communication means we stick to the OSI model. So we have a question: is there any routing protocol within the SAN network to allow communications between two storage networks in different networks? Yes, there are many options for this. So there are many options to communicate with different SANs, to extend SANs, and also communicating all the hosts between them. I will not go into that depth today, because I just want to let you know about how to connect to a fiber channel network in the first place. So there are a lot of technologies, yes, to extend fiber channel networks. And another question: what about FCOE? So last time in a free lecture, we talked about fiber channel over Ethernet. Now I always tell people that fiber channel. So imagine I have a server and I have a switch that has an Ethernet connection, right? Just a normal Ethernet connection. It's running multiple VLANs across here. So just a few VLANs. And then somebody came up and said, all right, so we have that separate fiber channel network running to all our servers with separate cables. That's a lot of cabling. We need to simplify that. And the way to simplify that is by using another wire that we already have to transport that storage protocol. And you said, well, in the first place, we started out that we wanted to have a separate physical network, right? That is still true, but in the meantime, the Ethernet will also enhanced, and now we are using 10 gig links here. And because we have so much bandwidth now to servers, we can start using that single wire to do both the storage protocols and the Ethernet protocols running across the same wire. So they said 10 gig should be enough for most servers, and otherwise we can start bundling stuff, bundling multiple links together, and then we save a lot of cost by not having to build all kinds of access layer switches to do the fiber channel forwarding, and not having to drag all kinds of fiber connections between the access layer and the servers. So what is fiber channel over Ethernet? This is fiber channel over Ethernet. So we remove that wire and that switch, that separate switch, and we built that technology into the Ethernet switch. So this has to be a new switch. Your access switch needs to be a new switch because it needs to support fiber channel over Ethernet. Examples of that are, of course, the Nexus 55K, Nexus 6K, Nexus 7K, all kinds of Nexus switches support fiber channel over Ethernet. What do we do with that? A lot of people think that fiber channel over Ethernet is just making an end-to-end connection between the host and the disk running across Ethernet. That is not the case. Fiber channel over Ethernet is a hop-by-hop connection. Why? Because this fiber channel forwarding logic, or FCF, is now being inserted into that access layer switch. So we do not change anything about the fiber channel protocol itself. So we just transport normal fiber channel frames. But what we do is we tunnel it inside an Ethernet circuit, inside an Ethernet VLAN. So what we do is we take the fiber channel frame, and what we do is we stick a .1Q header in front of it. And of course then some Ethernet headers. That's what we do. We tunnel fiber channel traffic with an Ethernet header towards the next hop, That next hop will take off the Ethernet header and will go look at the fiber channel frame and can then make its forwarding decision if it wants to switch it out the fiber channel network or maybe another FCOE port. So FCOE is just tunneling fiber channel over Ethernet. It's not an end-to-end connectivity, it's hop by hop. So connections to other switches here, if I would have another FCOE switch here, I would have an Ethernet circuit and another tunnel for a fiber channel across it. And then do the other lookup. So I first take off that Ethernet frame, do my fiber channel lookup, and then forward it out again. Just like I would with my Ethernet traffic. So it's just a tunneling mechanism to simplify the amount of wires in your data center. And of course separate equipment, because now I only have to buy one box that can do both Ethernet forwarding and fiber channel forwarding. I used to have to buy two boxes for that. But a lot more on FCOE, we will touch just fiber channel. So all the knowledge you have about fiber channel will stay in place when you're talking about FCOE, because FCOE is just a tunneling mechanism. And a comment, no IP is involved. That's correct, it's just pure Ethernet. It's just adding one header, and that is the Ethernet header. There's no IP addressing in that. On FCOE talking. I want to go back to my original topic. So, like I said, fiber channel and Ethernet are both data communication protocols. What that means is they both comply to the OSI model. Remember our layer 1 to layer 7 approach on anything related to data communication. So I want to compare the differences of both Ethernet and fiber channel compared to the OSI model. So I'm not talking about IP, I'm talking about Ethernet plus IP. Because Ethernet and IP are kind of stick together, right? They usually run with the same thing. So take your Ethernet and your IP knowledge and then convert that into fiber channel knowledge. So let's make a bit of a diagram about this. We have a layer 1 network, we have a layer 2 network, and we have a layer 3 network. I'm only going to touch layer 1, 2, and 3 here. So what kind of comparison can we make on layer 1, 2, and 3 on both the Ethernet world and the fiber channel world? So first of all, we have signaling here. The signaling is completely different in Ethernet than in fiber channel. So this signaling is definitely never compatible with each other. It even means that I need to buy separate optics, separate SFPs. My ASIC needs to support that physical encapsulation. So I need new hardware to support that fiber channel framing. So I'm not going to cover all that signaling right here, that's going to be a waste of our time. We're just going to focus on layer 2 and 3. Now here comes the fun part. Storage people say fiber channel is a layer 2 protocol. Why? Because what is in layer 2? This is our so-called physical addressing information, right? Our MAC addresses in the Ethernet world. We do have physical addressing in fiber channel, but this is not used in the header. It is not used for forwarding traffic. So a lot of people say, all right, so the only addressing information in a fiber channel frame, that's my next layer, that's my layer 2 information. But coming back to the Ethernet side, on Ethernet and IP, on layer 3, I configure my IP address, right? And my IP address is a logical address. My logical address means this physical address is given to me by the vendor of the network card or the switch port. This logical addressing is something I configure myself, or I get assigned through DHCP. So I get, this is an own configuration that I put on a given port. If I take a look at fiber channel framing, I see that the addressing information in the fiber channel frame is a logical address. I configure that myself. It is not given to me by the vendor, that is. I will come back to the details about this in just a few minutes, but I want you to understand that if you read storage books, they tell you Fibre Channel is a layer 2 protocol, but if you want to be able to compare it to the IP world, I say Fibre Channel is a layer 3 protocol without a layer 2. So we have no physical addressing in the Fibre Channel header. We only have logical addressing in the Fibre Channel header. So what kind of terminology do I use for those things? So like I said, we have our physical addressing. On the Ethernet side, they're called MAC addresses. Now what are MAC addresses? What can I do with a MAC address? I can, first of all, identify the NIC. So every network card, every switch port has one. Every switch has one. So every card has one, every switch port has one. But also the switch has a system MAC address. So a switch has a generic MAC address used in advertising things like spanning tree. So everything in the Ethernet world has a MAC address. Not everything has an IP address. Same thing here in Fibre Channel. So the MAC address is there to identify the physical thing, the physical port, the physical switch port, the physical switch. In the Fibre Channel world, we have kind of the same thing. We call them worldwide names. They are called worldwide names because they follow the same concept as MAC addresses, meaning they are unique globally. They are globally unique. A vendor gets assigned a certain block of worldwide names and can then assign its equipment with those addresses. So a MAC address and a worldwide name are comparable in terms of how they are handed out to the vendors. They are also there to identify exactly who is which device. And again, every NIC, every switch port, and every switch has a worldwide name. So same principles here as in the Ethernet world. A NIC in the Fibre Channel world is called an HBA, or host bus adapter. It's just a different name for the same thing. It's the network interface card, the interface to the network, but it's called an HBA. In the Fibre Channel world, there are multiple worldwide names per device. So in a MAC address, one port has one MAC address, the other port has another MAC address. With worldwide names, we distinct that difference between port worldwide names and node worldwide names. And we also have a thing called a switch worldwide name and a fabric worldwide name. So we have a number of different worldwide names. They all have the same addressing information. So it's a 64-bit address placed in hexadecimal characters. The port worldwide name is something that all the HBAs have. So every network interface card in the Fibre Channel world has a port worldwide name. So every disk, every port on the disk, every port on the host has a port worldwide name. Switch ports have a fabric worldwide name. So it's kind of the same thing. Every port has a worldwide name, but on a switch you call them fabric worldwide names. So not a difference in the addressing scheme again. Switch ports are just called fabric worldwide names. Then each host on the network also has a node worldwide name. So this is the HBA port, and the node worldwide name belongs to the HBA itself. So if I have a card which has two ports, an HBA always has two ports by the way, then I will have two port worldwide names. So each port will have its own worldwide name and one node worldwide name to identify the host or that card on the network. So everybody has two worldwide names, a port worldwide name and a node worldwide name. And of course, for as many ports as I have, I will get more worldwide names. Then last, the switch worldwide name is just that the same as the system MAC address. So that is comparable to the MAC address used in spanning tree root bridge allocations, root bridge elections. So those kinds of things, that's where the switch worldwide name is used. One MAC, one worldwide name for a whole switch. So kind of a node worldwide name for the switch. So the top two are related to hosts on the network, and the bottom two are related to switches on the network. Those are my worldwide names. And again, the question, does each HBA have a node worldwide name? So a different node worldwide name for each HBA. That is correct. Just like I showed you here, this is my HBA in a server. So that's my PCI card here that I stick into the server. That has one node worldwide name and two port worldwide names. If I insert another HBA into the PCI bus that also has two ports, I stick that in the same server, I will get another set of these addresses. So again, two port worldwide names and one node worldwide name. Question, how does a port worldwide name is assigned to a VHBA? This is handed out by the hardware vendor, just like a MAC address. So when you buy the when you buy the HBA, it will have these addresses configured. It will have them burned in, just like the MAC address. If you buy a network card, it will have a MAC address. Same with this. So the vendor allocates the worldwide names, the card vendor or the switch vendor. So again, this does not talk about where this is used in the forwarding of traffic, just to identify a host on my network. So worldwide names are there. So in the Ethernet world, they are used for both identifying, but also in the address format. So you also forward traffic based on MAC addresses. In the fiber channel world, identification is the only feature of the worldwide name. It's only there to identify a host. So this is your number. This is your port number 1, your port number 2. I just want to give everybody a number in the system so I can use that when I need to reference to it. Just there for identification. Then, what is the actual addressing in fiber channel? Actual addresses in fiber channel are called fiber channel IDs. So the name is kind of confusing because the worldwide names are used for identifying, and the FCID is the actual IP address, as you can call them. So my actual address, the actual address that I assign to a host to be able to forward packets. A question, have I explained about the types of ports used in FCOE? Not yet, no. This has nothing to do with FCOE. This is pure FC, remember? Pure FC, not FCOE. And I will come back to the port types later. I just want to focus first on the addressing information. So FCIDs are my addresses used to forward packets in the fiber channel network. They are consisting of a 6-byte format. So I have 6 hexadecimal characters that I can assign to, that I can use for addressing. So this is the format. So the 0x and then 6 characters, 6 hexadecimal characters. This FCID is always handed out. It is always dynamically assigned. Nobody configures its FCID physically. And it is assigned based on the switch port that I connected to. So there is a direct relation between the switch port and the FCID that will get assigned to the switch port. What that means is every fiber channel switch hands out addresses, so assigns addresses. Meaning every fiber channel switch is kind of like a DHCP server. It's not DHCP, it's totally different, but it's comparable to a DHCP server. It will assign FCIDs. So how does it do that? If I take my HBA port, I get a new server. It has an HBA. I insert that port into a switch port. How will the host get its FCID? So let's roll that switch. So we have a switch, just a fiber channel switch. Remember, not talking about Ethernet, pure fiber channel. And I buy a server with a HBA. And I drag a fiber channel cable between there. So a fiber cable with fiber channel SFPs. The server, as soon as the link comes up, the server will report itself to the network. It means it will log in to the network. This process is called fabric login or FLOGI. So not talking about port types yet, just link comes up, every host in the network needs to report itself to the network. Hey, here I am. That is a requirement in the fiber channel standard. So it's not like Ethernet, hey, you connect to me, I'm going to be quiet until you say something. No, this is based on the standard. So every host needs to perform a fabric login before it can access anything in the network. What will it do during the FLOGI? It will first of all say, hey, this is me. These are my worldwide names. So port worldwide names and node worldwide name. Then it will ask for an FCID, or actually the switch will just give him an FCID. That is because every switch has a block of addresses assigned to it. Every switch will get a block of addresses assigned after the first 2 bytes. So these first 2 characters in the FCID, those will be that block of address. Everything behind those 2 characters is assigned to a single switch. How will that get assigned? I will talk to you about that in the next minute. So I assign a block of addresses to the switch, and now that switch can be authoritative on that certain block of addresses. And it will hand out an address to the host, to the server. It says, all right, you did a FLOGI to me. I will report back to you with the FCID that you need to use. So the switch will report back with an FCID. Question, is it similar to a DHCP pool? It is very comparable to a DHCP pool, yes. So every switch in the network has its own DHCP pool and assigns addresses from that. So if I move a host, so if I take that server and I connect it to another switch, it will get a new FCID. I cannot do static FCIDs, for example. I technically can do that, but nobody uses that. If I take it to another switch, I will get a new FCID and I will log into the network again. And based on my worldwide names, I will detect, of course, what host it is and that I saw it before. And then all the configuration that I did to allow that host to go somewhere will stay in place. Question, all the FCIDs are pre-configured in the switch? No. That's the next part. So this is just the host to switch login. What I now want to talk to you about is how do the switches assign these FCIDs. So I want to focus on the fiber channel framing first. What is fiber channel framing? So I take a data packet. Inside this data packet, what is in there? In there is a SCUZI command. SCUZI is the de facto standard for exchanging data between a host and a disk. So a SCUZI bus can be inside your local server, or it can be used to communicate on longer distances. So this is the normal SCUZI protocol that you're used to, that local disks in your server are also using. Therefore, it is so easy to implement this and use that for long distance links. Or in fact, use that for a SAN feature. Because the server doesn't need to talk another protocol. The server just talks SCUZI to a disk. And actually, it will think the disk is just inside its system. So the SCUZI command is the data packet. So this is either a read action, of course, or a write to a disk. So the SCUZI command is inside the data frame. Now, looking at the fiber channel frame, there are, of course, some other fields in there to identify some of the traffic that's in here. Something called an exchange ID, for example. Every SCUZI read and write action will get a new exchange ID. So every read or write in the network will have its own exchange ID. And based on that exchange ID, I can do fragmentation. Remember, if I have that big chunk of a 20 gigabyte file that I want to collect, I will not be able to put that in a single packet. I need to fragment that in multiple packets, just like Ethernet. So comment, SCUZI actually provides the communication between the network and the disk. Well, between the server and the disk, yes. So the server just talks a SCUZI command to a disk, and in between there is fiber channel communication. But the SCUZI command is exactly 100% equal if you would run SCUZI in your disk locally or SCUZI on the fiber channel disk. So the exchange ID is used for fragmentation. Things that belong to each other, so parts of that 20 gigabyte file, will all share the same exchange ID. And that number is just assigned by the HBA or the switch or the disk. So a good comment, the network part is replaced instead of the direct pinning cable, correct. Instead of a direct cable, you're now using a full network. So, before the exchange ID, in front of the exchange ID, I have two numbers. I have a destination address and I have a source address. Thanks. The question, does it have a mechanism like retransmission in case of a frame drop? Now this is the cool part about Fibre Channel. Fibre Channel will never drop a frame. So there is no retransmission in here because it's not necessary. The protocol itself is lossless because it implements a very cool form of flow control. We know we won't have enough time today to talk about that whole flow control principle, but assume Fibre Channel will never drop a frame. Same for FCOE, by the way. FCOE doesn't drop a frame as well. So coming back to my framing, I have a source address and a destination address, just like I would have in an Ethernet header or in an IP header. Remember, this is logical addressing here. So here I put the destination FCID, so 010011, and there I put my own source address, which is 102AB9. So logical addressing is in the frame. The worldwide name is not included in the fiber channel header. The worldwide name is not there. The worldwide name is just there for identification, and I will show you how you use the worldwide name to identify certain things. The question, FCOE is a combination of FC and Ethernet. Exactly. Just what I touched here briefly. FCOE is just a tunneling mechanism for fiber channel frames, the full fiber channel frame with all the headers and all the addresses in place. And I add an Ethernet header to that. Just like I would stick traffic into a GRE tunnel, for example. As a very stupid comparison, but it is tunneling of the full fiber channel frame into an Ethernet packet. That Ethernet packet takes the fiber channel frame to the next hop. So the switch, from a server going to a switch. There, the Ethernet frame is taken off, and I will look at the fiber channel header to make my forwarding decision. I don't take a look at the Ethernet header, because the Ethernet header is just addressed to me. It's addressed to the switch. And now we have a very good question saying which mechanism monitors so that two switches do not use the identical IDs. So I will come back to that in just a minute. So again, this is my fiber channel framing, no worldwide names. Next, I want to talk about the addressing. Like I said, every switch in the network will get this block of addresses assigned. That is that first 2-byte header, or header that's the first 2 bytes of the FCID. Those first 2 bytes are called the domain ID. So every switch in a network has a domain ID. This is just a number, can be number 1, number 2, number 15. And every switch has that number. And that number is used to allocate the addressing information. The second part of the number is called the area ID. And the last section is called the port ID. Now, there are a lot of discussion on how to allocate FCIDs. Like I said, a switch will always get this block of addresses. So a switch has a domain ID configured, or it gets assigned a domain ID. And then it has this full range of addresses that it can use to allocate to hosts. When a flaggy is done, a flaggy comes in from a server, it means that I will start allocating an address. So first of all, I put my domain ID in front of here. That's going to be the first part of the address. Next part is going to be I will assign an area ID to it. So just I will assign that myself. So port 1 will probably, the first flaggy will get area ID 1. The second flaggy will get area ID 2, and so on and so on. There's no such thing as network addresses, broadcast, subnet masks. That's no such thing. It's just an address. And then next, I assign that full range of addresses, that full range, that full area ID, I assign that full area ID to the host. Why do I do that? Why do I give the host the freedom to choose its own port ID? Well, if you take a disk array has a link, so an FC link to the network, and a lot of disks are in that disk array. So disk 1, not a disk, disk. This array will do one flaggy. So there's going to be one flaggy request. So now, after that, the array will need to assign each disk with an FCID itself. So the disk array will get this block of addresses assigned. So one flaggy is seen from a normal disk array, depending on the type, by the way. And then it will assign a port ID to each of the disks. So just assume, or just know, that once a flaggy is done, this is allocated to a switch port, and that is answered in the FLAGI reply. Now, like I said, every switch has a domain ID. The domain ID needs to be configured, or it's dynamically assigned. So, again, forwarding. What if I have multiple switches in my network? I have a number of fiber channel switches in my network. Can I repeat what specifically? So we have a question. It can be of a maximum of 256 ports, as an area ID is only 1 byte. No, it's 2 bytes. So I have 16 characters. No, sorry, it's 1 byte. You're correct. It's 1 byte. So correct. So if you have switches with more ports than 256 ports, it will not allocate the full block to all the ports. It depends a little on the port type. There are not that much. There are not that much switches with over 256 ports, right? So it's just a single box. You can have a huge fiber channel switch with multiple line cards that can run over that number, and they have a little trick for that. I cannot go into that detail right now. It's a little trick that they do, where they will not allocate the full block of, then they will not allocate the full area ID. Another question, a domain ID is per vSAN. I will not touch vSANs right now, but yes, a domain ID is per vSAN. About the communication of the diagram of the disks. What I said here is, my disk array, so the whole rack is filled with disks. That disk array will have one connection, or two of course for redundancy, but assume one connection. And on that one connection, it will send a FLAGI request. It will do one FLAGI for all of its disks. And it will get one area assigned, so 10, 10, 11, 00. And the disk array is free to use any of the numbers in that address. So it can, by itself, it will assign a port ID of 1 here, port ID of 2 there, and then this disk, if this disk wants to communicate, this disk will specifically have the 010101 address. Next disk will be 0x010102, and so on and so on. So that is why I assigned that whole area ID to a port. So question, switch 1 has a domain ID of 1 in vSAN 1, and switch 2 has the same domain ID in vSAN 2. Will it be considered overlap? No, totally separated, just like Dominic already said. It's a totally separated configuration. But unfortunately, I cannot touch vSANs right now. So we'll go back to our domain IDs. Like I said, imagine all the domain IDs are assigned or either configured. I will go into the assigning of domain IDs later. So this switch is domain ID 1, domain ID 2, domain ID 3, and domain ID 4. So how will their FCIDs look? 0x01, 0x02, 0x03, and 0x04. So those are going to be my domain IDs. What happens if I get a packet on one of my ports, and that packet has a destination address of 0x04, 0201. So just a made up FCID. That is the destination address. This switch, what it will do is it will take a look at the first portion of the FCID. if it sees a 1, it will say, all right, that's for me. That's locally to me. So I will now forward that traffic out of a switch port. So it will start looking at its addressing table and send it out on a given port, on the correct port. But now it sees a different domain ID. That means it needs to route the traffic outside of the switch. There is no FCID learning like MAC learning. Fiber channel uses routing to get its traffic through a network. To get traffic from one switch to the other switch, it routes the traffic. Meaning I forward traffic out a link where I know that the switch is behind. How do I know that? I run a routing protocol. It is based on OSPF. It's actually not called OSPF, it's called FSPF. I run a routing protocol between my switches. I do not run the protocol to my hosts because all I advertise in the routing protocol are domain IDs. So every switch will just do a link state update to the rest of the network where it will say, hey, I am domain ID 1 and I have domain IDs these connected to me. So everybody will have a full view of the network. Every domain ID is seen in every switch. So I run routing protocol. There is no need to configure this, by the way. This is all done automatically. As soon as I bring up a link between two switches, I have the communication established. I have a routing adjacency established. And I will start building a topology. What this means is, it will check its fiber channel routing table to see where is domain ID 4. And there it will see domain ID 4 is behind switch 2. So I will forward it out going to switch 2. Switch 2 will do the same lookup, going to switch 3, and then finally go to switch 4. On switch 4 it will arrive, it will see, hey, this is my domain ID, so I will forward it out locally. Again, not going in depth on FSPF, but assume it's a routing protocol. I route fiber channel packets. Now, because this is a routing protocol, I am running into a scalability limitation. Because of course the CPUs in these switches will need to build their own shortest path first tree of all the switches in the network. So depending on the switch type, there's also only a maximum number of fiber channel switches that you can stick together, that you can connect to each other. We have a couple questions coming up. A question, if manually configuring domain IDs, is CFS used to check the existing domain ID is not already in use? No, but that's actually the next topic that I'm going to talk about. So again, domain IDs. A domain ID can be either statically configured or it is assigned. In both ways, I need to ask permission to the network if I am allowed to use this number. So either way, I need to have permission of the network to run a certain domain ID. I cannot just configure one and have an overlap with somebody. Domain IDs will never overlap. Why? Because you always need to have permission. How do I get permission? What I do in the fiber channel network is I assign one switch to be the master of the network. And as already mentioned in the chat window, this is called the principal switch. So the principal switch is the switch that will determine who will get which domain ID. that principal switch needs to be elected. Just like a spanning tree root, actually. It works kind of the same way. So as soon as new links come online, so two switches will connect to each other. They will not do a floggy to each other. That's a thing that only hosts do. They will do other communication packets between them, like running the FSPF protocol and stuff. But before that, they will run a principal switch election. Again, that is of course based on a priority value plus the switch worldwide name. Just like in spanning tree, right? Priority value and the system MAC address. And also here, the lowest one wins. So yeah, you can say that fiber channel is more based on domain IDs, correct. At least in forwarding perspective. Domain IDs are very important for your forwarding. So I elect one of my switches to be the principal switch. That principal switch will now be, everybody will know about that, so it will advertise between all the switches in the network. I am now the principal switch. It is not a preemptive role. So if somebody else with a better priority comes online, we don't care. We stick to our principal switch. And as soon as that dies, I will elect a new principal switch in my network. Question, is there any backup principal switch available? No. There's only one principal switch, and if that dies, the next best priority value will become the principal switch. So there's not a real backup, but there's not a real state that needs to be exchanged. Because all the switches in the network are authoritative on their own piece. So there's not a real exchange that needs to be done. And the failover is pretty fast. So a question, all the principal switch does is manage domain IDs. No, I'll come back to that later. So this is one role of the principal switch. One of the roles of the principal switch, so it's just any of the switches, right? I can just assign one of these switches. It doesn't matter where it is. I don't care because it's never going to do something in forwarding, right? Because the routing protocol takes care of the forwarding. So I can make this switch, I can make this one the principal switch. Because it's like spanning tree, the spanning tree root will influence how the forwarding topology will look. That's not the case here. The principal switch is just a management role. It's just a CPU role, a control plane role. And one of the things it does is saying yes or no to the request for running a certain domain ID. So once I bring up a switch and I do not configure anything, what I will do is I will request a domain ID of 0 on the network. A domain ID of 0 is invalid. That's not a real domain ID. So you never have domain ID 0. The request will reach to the principal switch, and that will assign a number which is not yet used. So it will answer back. The reply will be use domain ID 123. So that's a good way. That's a good thing to do that. You can do that. So actually the fiber channel network is pretty self-learning. I just connect some cables, I connect things to other switches. As long as I make sure that my ports are properly configured, everything will come online in terms of control plane. I do not need to configure the routing protocol. I do not need to configure the principal switch. I do not need to configure the domain ID. Everything will get assigned automatically. Now, if I want to have some control over it, maybe I want to have some control over domain IDs that get assigned, I can statically configure it. I can statically configure it in two ways. Both ways need to ask permission to use that domain ID. So a true static configuration doesn't exist. Question. If the non-principal switch gets assigned a manual domain ID of 10, let's say, and later you want to do the same value on the principal switch, So the principal switch will deny this and assign it to itself. No, actually. So if the domain ID 10 is already taken, well actually, in the end, the principal switch will take that number, because what will happen is, I have two switches, both have domain ID 10 configured. I will bring up a link in between, and then a principal switch selection occurs. That's the first thing to do. So this switch will become the principal switch, and of course it will answer its own domain ID request first, before answering the other guys. So it will do its own domain ID selection first, before replying to requests. If I have an existing network with a principal switch with domain ID 10 and domain ID 12 here, I connect a new switch that also has domain ID 10 configured. Well, now the principal switch is already elected, so it will get a new one. So will it take precedence? Protocol-wise, no. It's just that it will run the principal switch selection first, and then of course it's going to reply to its own requests first. So yes, both configured as 10. The one that will get assigned the principal switch role will get domain ID 10, and not the other guy. So again, how do I configure static domain IDs? I can configure them in two ways. Either static, that's what I said, right? Static, or preferred. What's the difference? I have this network. I connect a new switch, so the principal switch is elected. I set here a static domain ID or a preferred domain ID of 12. Now that domain ID is already taken. So I do that preferred request to the principal switch. The principal switch will say, no, that's not good. 12 is already in use, but instead use number 14. This is the reply from the principal switch. The 12 is sorry, you cannot use 12. If 12 was freely available, I would be happy to hand you out 12, but I do not, so I hand you out 14. So if 12 is available, it will always get 12. If it does not get 12, it will honor the request from the principal switch and will use 14 now. Now another switch comes online. It has 12 configured statically. It will do the same request. I need 12. The reply from the principal switch will say, no, I do not have 12 for you. You can ask for it, you can demand it, but I do not have it for you. So I reply with a no. I reject your request. Now what will happen with this switch? This link will go in isolated state, so it will just shut down the link. So that switch will not be part of the network now, because the domain ID is already taken, and my configuration says I can never use another domain ID. So I'm stuck, right? I cannot use it, and so I'm stuck. So I'm going to isolate that port. So the preferred one, the link will always come online, maybe with the correct domain ID or maybe not. Statically assigned. If the domain ID is available, I will get it. If not, I will shut down my port. Question, is a domain ID stored in NVRAM across a reboot once assigned? No, so there is a difference. I have a configured domain ID and I have a running domain ID. So I might have a configured domain ID of 12 preferred, and I have a running domain ID of 14. This is saved in the RAM, and this is not saved in the configuration. So once the switch reboots, it will again be part of the network and say, hey, I want 12. And the principal says, no, you cannot have 12, here you have 14. So this is not saved in the configuration now. It's not saved across reboots. It's just like a new switch gets connected. Because the links will come up, I will start requesting for domain IDs and stuff. So those are my domain IDs. So now every switch in the network has a domain ID assigned by the principal switch, and now we build our routing table, and now we start forwarding traffic. So we have a couple of questions coming up, as it seems. So we have a comment, that's why we zone based on the port worldwide name and not on the domain ID, because the domain ID could change. That is fully correct, and that's actually the next topic that I want to talk about. So what's the relation between worldwide names and FCIDs and domain IDs? So I said to you, I have two switches. Switch 1 and switch 2, so domain ID 1 and domain ID 2. I have a server, server 1, and I have a disk array called disk 1. Server 1 and disk 1. Alright, somebody needs to leave, so thank you, bye-bye. So I have a disk 1 and I have a server 1. Domain ID 1 and 2 are assigned. So this server will have FCID 0x01, 1A01, some domain ID. The disk will have 0x02, DA01. So those are the two FCIDs. Then I said in the fiber channel frame, they need to specify that source and destination address that they want to use. How will they learn about that? Because I just do a flaggy, I get that FCID assigned. The switch is locally administering those FCIDs. So now nobody knows who is what, right? How do I know how to get to the destination FCID? There is a concept in fiber channel that is known as for the address resolution. What is address resolution in Ethernet? I use ARPs. I send out a request to the network saying, who has 10.0.0.1? And I will get a reply saying, this guy is it with this MAC address. And now I can start forwarding traffic. So I want to have a bit of the same concept here. But first of all, I'm probably going to be unaware of this guy's worldwide name. So remember, we have the port worldwide name here, and we have a port worldwide name there. I'm unaware of that. Or maybe I am aware, but I still don't know the FCID. Maybe I know the worldwide name of the disk. Well, because as a good comment that was given by Dominic, this FCID changes if I move the disk around the network. So if I might migrate that to another switch, I need to redo all my programming. So this server might or may not know the worldwide name of the disk. Assume it knows the worldwide name. So it will request who is port worldwide name 1234. It needs to get a reply. We do not have a thing called ARPs in fiber channel. We do it in a much more scalable way, in a much better way actually. You really see that fiber channel has been developed much later than Ethernet. Why? Because a lot of these things that needed to be fixed in Ethernet just work in fiber channel. They took a look at the application world. How do applications do address resolution? I say google.com. So actually this is the same thing. So how do I do logical address resolution in the IP world? I say google.com has 11.1.2.3 as an IP address. This is DNS. Fiber channel has the same concept as DNS. So instead of a DNS server, I have a fiber channel name server in my network. That's how I do address resolution. I send a request to the name server saying, hey, who has port worldwide name? So what does the FCNS do? The fiber channel name server has a list of port worldwide names with FCIDs and nothing else. So it says port worldwide name 1234 is 0x011A01. Port worldwide name 5678 has 0x02DA01. Just DNS entries. And of course, like I said, domain ID assigning is one role of the principal switch. Running the fiber channel name server is another role of the principal switch. So the fiber channel name server is running on the principal switch. Actually, this is the authoritative guy on the fiber channel name server. Every switch in the network will have a copy of the fiber channel name server database in its memory. So the FCNS database is being distributed to all the switches. So as soon as I need to do a failover, if my principal switch dies, I elect a new one, I already have the fiber channel name server database. So that's why there is no state exchange between so that's why I do not have a backup principal switch, because I already distribute all that information to all my switches. So the principal switch is the one who will respond to the queries. How do hosts register with the name server? We talked about floggies, right? During the fabric login, we get assigned our FCID. The next step that a host does as soon as it becomes online on the network is it will send out a port login or pluggy to the principal switch. Or actually, it's going to send it to a certain address, and the principal switch is the one that's going to reply to that. So the port login is being replied to by the principal switch. And you can compare this to registering with the DNS server. So imagine a Windows PC in an Active Directory network. I log into the PC. As soon as I do that, the server will register itself with the DNS server, saying, hey, I am hostname this is my IP address. That's the same thing that this host will do on the fiber channel network. It's going to send a plugin, and in that plugin I'm going to say, hey, I am worldwide name this, so port worldwide name, and this is my FCID that I got assigned. And it's going to register that with the name server. So cool, right? A lot cooler than Ethernet. So fiber channel name server. Just a table with worldwide names and FCIDs. So what happens when I want to do forwarding of traffic? This server knows 1, 2, 3, 4. It says, I want to get access to port worldwide name 1, 2, 3, 4. If you have a comment, please upload this session on YouTube. We will definitely do that. So either tomorrow or the day after, this video will become published on YouTube. So back again. This server knows about the port worldwide name of the disk. So the server guy talks to the storage guy and says, hey, what's your worldwide name? The storage guy will reply to him, hey, this is my worldwide name. So just on paper, right? They walk to each other's desks, exchange the information. And now this guy on this server will configure, I want to access the disk with worldwide name 1, 2, 3, 4. This is going to go into a query to the fiber channel name server. And that FCNS is going to reply with the correct FCID. So now the server knows exactly what the destination address should be and of course what its source address should be. So the destination address is 0x02DA01, source address of 0x011801. This packet will arrive here at this disk because again, switch 1 will look at the destination address. It will see a domain ID of 2, so it's going to forward the packet out to 2. 2 is going to receive it. It's going to look at the domain ID. It says, all right, hey, that's from me. It's 02. What is the area code? DA. I registered that code here on port number 13. And I'm going to send the packet out on port 13. So that is how my connection is established. I assign a domain ID to the switch. I assign FCIDs to the hosts connected. And the hosts will register themselves with the fiber channel name server. And that is how I establish end-to-end connectivity in fiber channel. Not talking about access control, not talking about port types yet. So this is my end-to-end communication of fiber channel traffic. So what does the principal switch do? Assigning domain IDs and be administrative of the fiber channel name server. All right, that's about forwarding. I want to talk a little bit about access control. Because by default in a fiber channel network, nobody has access to talk to anybody else. So that's totally different from the Ethernet world, right? In Ethernet, it's just, hey, talk to each other, please, talk to each other. In fiber channel, no communication whatsoever when you boot up. I do not communicate with anybody else in my network unless I specifically have given permission. So what I do is in my fiber channel network, I will build access lists. Kind of access lists. This concept is called zoning. Zoning are access lists for switches, for fiber channel switches. So I need to specify in my zone that host server 1 and host disk 1 can talk to each other. That's what I need to specify there. There is such thing as a zoning database. And there is always going to be one zoning database in the network. There's one database in the network, so everybody can change it. So again, going back to my 4-switch topology. Everybody has a copy of the zoning database. So that's all good, right? Everybody has the copy and everybody can change it. Everybody can start editing the zoning database and then applying the changes to the network. So as soon as I apply this change to the fiber channel network, everybody will receive a new copy of the zoning database. And of course, who controls that? The principal switch. So the principal switch administers the zoning database. It doesn't mean I can configure it from anywhere, but as soon as I activate it, so as soon as I publish the changes to the network, the principal switch will make sure that everybody gets a copy again. The question is that the active zone set, that is correct. That is the Cisco terminology for that. So how do I configure a zone or zone set? I configure a zone set, and this is my container that I can use to configure different zones. I then specify a zone, zone 1. or zone A, or zone RIC, or zone IP expert. In that zone, I'm going to specify exactly which two hosts or which multiple hosts can talk to each other. So I specify server 1, disk 1, and disk 2. Now by specifying these three entries, it means that everybody can talk to everybody. All the members in the zone can talk to each other. If I configure a new zone, they cannot talk to each other again. So here is server 2 and disk 3. Zone number 1 and zone number 2 have nothing in common. They do not share anything. I'm just saying permit IP address 1 to 2. So the question, if I make a change on switch 3 and switch 1 is the principal switch, then my changes first go to switch 1 for propagation to the rest of the fabric. Yes, that's correct. So the principal switch will make sure that everybody gets the copy and everybody gets the full zoning database. And how that communicates, there are a lot of packets that need to go back and forth to do that. But that's correct. So again, things, hosts and disks, or servers and disks inside a zone can talk to each other. If you split them up in different zones, they cannot. So I just make access list entries here. One zone is one access list entry. And to combine that, I configure a container called a zone set. And what I need to do to ensure, so I start editing this, and as soon as I'm done with that, I will activate the zone set. And as soon as I type that zone set activate command, I will publish the changes through the network. Question, can devices exist in more than one zone within the active zone set? Definitely. What is actually the best practice for configuring zoning is configure one server and one disk in each zone. So there might be one server that wants to access multiple disks, right? Multiple targets, that's called. So I configure each server and disk in a separate zone. So server 1, disk 1, server 1, disk 2, server 1, disk 3. All different zones. So to be very strict in the access control that I do. Same accounts for disks. Everything can exist multiple times as long as they are in different zones. Because every time I'm allowing a different entry, right? Every time it's a different access list entry. So that is access control. How do I determine that? And because I know, so every switch knows exactly that because everybody has a copy of the zoning database, every switch will say, all right, server 1, it has 3 zones in which it allows access to disk 1, disk 2, and disk 3. So everybody knows exactly, so the switch knows exactly to which disks this server 1 has access to. So what you can do now is, if I have my host again, my server 1, I can, if I do a name server query, so I query the fiber channel name server, and I can do that with some kind of a wildcard. So I can ask the fiber channel name server, what do I have access to? Give me a list of devices that I can access. And by use of the zoning database, that reply will say, hey, you have access, hey, you server 1, you have access to disk 1, disk 2, and disk 3 because of the zoning configuration. That is a reply that the fiber channel name server, so the principal switch, will get. So here is also a big difference in soft zoning and hard zoning. If you're a Brocade guy, this is going to change your way of thinking about soft and hard zoning. But I believe you all are Cisco guys, so nobody will have an issue with this, understanding this. Soft and hard zoning on Brocades means a little bit different thing. But this is the actual standards-based soft and hard zoning. What is soft zoning? Or let me say hard zoning. Hard zoning says I give you a custom fiber channel name server reply, right? So I just reply with the disk that you have access to, and I will make sure that you will not be able to communicate to the disks that you cannot access. So do you try to reach switch 4? Do you happen to know the FCID of disk 4? I will make sure that you cannot communicate to it. In soft zoning, all I do is spoof that fiber channel name server reply. So I will only reply with, hey, you have access to disk 1, 2, and 3. But if you happen to know the fiber channel ID of disk 4, I will not limit you by doing that. All the switches by default use hard zoning. Nobody uses soft zoning. But that's the difference. There were, in the beginning of fiber channel, there were some switches that could not do hard zoning, but only soft zoning. But that's no longer the case. But that difference is still important to understand. So that fiber channel name server reply is always going to be customized to the zoning database. And with hard zoning, I even prevent communication between everything. So that is soft and hard zoning. And the last thing that I want to touch are port types. So we talked about forwarding, we talked about worldwide names, we talked about FCIDs, we talked about domain IDs, we talked about the principal switch, and we talked a little bit about zoning. The last thing that I want to talk about is port types. In the fiber channel world, I need to specify on a certain switch port what type of port it is. Because after that, it's going to do some different things, right? If I connect to an E port, it means that I need to set up the FSPF protocol. I need to do a principal switch selection. If I set up a port going to a host, it means I'm going to expect a floggy. It means I'm going to expect a ploggy. It means I'm going to expect other communication than I would have between switches. So you can compare this to, let's say, configuring access and trunk ports in the Ethernet world. It's technically not the same, but it's kind of the same thing, right? An access port is a host, a trunk port is an uplink. Take that logic and take that here. But forget what it does technically. The two most important port types are fabric ports and extension ports. So F and E ports. An F port always connects to a host. So this is seen from a switch. So this is port types on a switch. Because from a host perspective, if I have that host here, this is my server 1 and my switch 1. On switch 1, I will configure this port to be an F port. On the host, this will be an N port or node port. So F ports always talk to N ports. But the N port, you never have to configure the N port because that's automatic. A server or a disk always is an N port. No question about it. So it's just that I'm configuring an F port here on my switch. So on the switch port, I say switch port mode F for saying, hey, on this port, I'm going to connect an end host. I'm going to connect either a disk array or a server, and that's going to be connected to me. You can guess the second port, the E port, is how I connect to other switches. So this is my trunk link. They call that the ISL, or inter-switch link. It has nothing to do with the encapsulation format from Cisco. On the Catalyst switches, this is just an inter-switch link, so a link between two switches. So on an E port, I'm going to automatically enable the FSPF protocol, domain ID, synchronization, all kinds of stuff. There are a lot of other port types, like trunking ports, NP ports, ST ports, SD ports. So there are things like ST and SD. They're used for span sessions and stuff. But let's just focus on F ports and E ports, because those are the only ones. Again, if you're used to Brocade, you will see more port types, but they do technically different things. Yeah, like an L port. An L port is something, oh sorry, an L port I can touch actually. In the past, it's not used a lot anymore, but in the past what they did was, I have a disk array with one fiber channel connection here and another there. And because I did not have switches in my network, or I had switches which were not capable of doing a lot of fiber channel forwarding, I could loop the disks together. So I could make a fiber channel loop. And loop things through the network. So these are our loop cables, and the packets are forwarded through each of the disks. This is still supported, so some disk arrays still have this kind of architecture internally. So they loop everything together and then go out on another cable. These are called also fabric ports, but these are called fabric loop ports. Because of course the traffic forwarding is a little differently. And now, instead of only doing one floggy, I expect to see a floggy from every disk. Because every disk is its own entity in the fiber channel network, but it is containing in a loop. So question, FL ports needed for JBOD connectivity depends on the JBOD. Some JBODs do support FL connectivity, others just are configured as F ports. It depends very much on the controller inside the JBOD. In the past, you also had TL ports. Those were private loop ports, but that's never used again. That's an ancient technology. So yes, FL ports needed for JBODs. You will see that when I start my demo. So I just want you to focus here on F ports and E ports, host ports and switch ports. So that is the theory that I want to cover. If you have any questions, please state them now, and then I can show you a little bit of the logic during the demo, during doing a little demo. We have a question, what is the TE port type? So a TE port type is what they call a trunking E port. Why a trunking E port? That has to do with the concept of vSANs, and I do not have enough time right now to cover that, sorry for that. So trunking E ports are trunking different vSANs across the same link. It's not a thing that you configure separately, but assume that it's there for just trunking multiple vSANs across the same link. Alright, so let's do a quick demo. I have some MDS switches, but unfortunately I lost connectivity. So, actually it's the wrong MDS. So question, are we likely to get told in the lab what port type will be needed for JBOD connectivity? Yes, you will. So they will either tell you, or you need to rely on, there is some auto negotiation. So a switch can detect what kind of port is connected to it. So if it sees a floggy, it will say, all right, so this is an F port. So it will see that. So there is auto negotiation even. Or otherwise, they will tell you that. No, I'm not breaking any NDA for that. I'm just saying they could do both. All right, so let's check. So this is an MDS switch. So again, we did not touch the hardware actually. But as you can imagine, Cisco has a separate portfolio for pure fiber channel switching, and the MDS is the product line for that. So this MDS switch only has fiber channel ports. FC1/1 up to FC1/14. So just pure fiber channel ports. And as you can see, by default, my ports are configured as auto. And auto means I can do auto negotiation on the port type. So you do not have to know exactly what you're connecting behind that. So what will we do? I will first bring up my host to switch connectivity. I have a JBOD connected to FC1/5, and I'm going to set this switch port mode to something. As you can see, there are a lot of switch modes. One of them is E, one is F, that's fabric loop mode, or some other things. Like I said, the TL are private loop ports, not used anymore. The SD and ST ports are used for span features. NP is used in a way that's called N-port virtualization. I will not touch that right now. And the FX mode is the same as auto, except it is not fully automatic. So auto is it can become any port type, and FX means it can become any F port type. So meaning F or FL, right? Is it a true F port or is it an FL port? That's FX mode. I know that my JBOD is a loop, so I'm configuring this as a fabric loop. And that's actually all I need to configure here. I'm just going to configure switch port mode FL. I can configure speeds, so I can set the link speed here. By default, it's going to auto negotiate the speed, and that's going to work fine. So I'm not going to change that. And for the rest, I don't need to change anything. I need to no shut the port. So if I do a show interface FC1/5, I will see my link is up. This is my fabric worldwide name. It's going to call it the port worldwide name, but technically it's called the fabric worldwide name, but it's technically the port worldwide name of this switch port. In the rest of the CLI, this is called the fabric worldwide name. So that's where the confusion gets you. And I see exactly what the FCID is that I assigned to this port. So I automatically assigned myself with a domain ID of B9, and I assigned area code 0 to this port. Here you can see the default and same maximum MTU size. So MTU size of fiber channel is always set to 2112. And that is also the maximum MTU. So what is the first troubleshooting step that you need to do to verify that your connectivity is established? I check if I have done a floggy, show floggy database. Question, is the area ID configurable at all, or is it always dynamically assigned? Well, first of all, it is always dynamically assigned, but yes, I can configure that statically. So that is true. When I reboot the switch, a little bit extra here, I have something called an FCID database. In that FCID database, I'm going to say this port worldwide name will always get this area code assigned. So this is actual configuration stored in Flash and persistent across reboot. So after a reboot, every port will get the same area code assigned again. And you can statically configure this as well. So technically, yes, you can statically configure area IDs. Good question. So first task that you do, as soon as you bring up a port, the command you do after that is show floggy database. Because in the show floggy database, I will see exactly what is the port worldwide name, what is the node worldwide name, and what is the FCID that I, the switch, assigned to that port. And you see exactly what it did. So it assigned the 00 area code, and it assigned 00 as port ID, and then the disk assigned to itself the E2. So this is a disk array with only one disk. So here's my floggy. After that floggy is being processed, like I said, I register myself with the fiber channel name server. So let's check the fiber channel name server. Show FCNS database. And here I see exactly what the port is. So I see exactly what the port worldwide name is and what the FCID is that belongs to it. So I do not see domain IDs here. I do not see ports, so interfaces, because I don't know them. The FC name server only knows about the port worldwide name and the FCID. Nothing else. And of course then the local switch knows about the FCID and about the local port where it needs to go out. If I do a show FC domain, I see that this switch is the principal switch. Well, that's true because it's the only switch in the network right now. I have a configured domain ID of 0 and I am running domain ID 185 or B9. So that is the difference between the configured ID and the running ID. And the principal switch is the one that will determine that. Default priority is 128 out of something between 0 and 254. 255 is an invalid number as a priority value. So any lower number is better. So priority ID 0 is the best priority that you can get. Same with spanning tree. Question: in your demo, there's only one device behind the FL port, so we can only see one entity in the fiber channel name server. If we had multiple devices, we would see multiple entries. That is correct. And I will now bring up another switch link to see that you will have multiple entries in the fiber channel name server. So now I only brought up an F port. That F port reported all its disks that it has, only one unfortunately, to the local switch and to the fiber channel name server. There are no zones configured yet, so nobody can talk to anybody. What I'm going to do now is I'm going to bring up an E port. I know that behind fiber channel 1/1 I have another switch. So my topology looks like this. I have MDS 1.1 and I have MDS 2-1. This one is connected to a JBOD with one disk. And here I have another JBOD with another 1 or 2 disks. I think also 1 disk. This is port FC1/5. This is going to be port FC1/5. This is going to be 1/1 and 1/1. So I'm now going to bring up this port. So I brought up port 5. That is okay, because I see the flaggy and I see the FCNS entry. Now I'm going to bring up the E port between MDS1 and MDS2. What do? I say switch port mode E. Oh, I configured the switch name right now. Switch port mode E. And for this example, I'm going to shut down the trunking, because otherwise the Cisco switches will default to a TE port. But I do not want to do that. I just want to run an E port. And I'm going to no shut it. I'm going to do the same thing on MDS2. Switch port trunk mode off, no shut it. Now if I check interface FC1/1, I see that it's still down, it's initializing. Sometimes it takes a while. So we had a question, how are these MDS switches connected physically? That's what I drew here, right? So this is my physical topology. Port 1 here, port 5 there going to JBODs, and I have the same setup here on MDS2. And now it's up. So now I see I am running in an E port mode and nothing else. So if I check my Floggy database, still one Floggy. E ports do not run Floggy. They run the Fiber Channel Routing Protocol, FSPF. In my name server database, I still only see one host, because there's still only one host on the network. But what if we do these commands on MDS2? Show floggy database. There are no floggies here. Why not? A floggy is only local to the switch. So it is its local FCID to interface mapping. So the floggy database is never transmitted across the fabric. Floggies are always local to the fiber channel switch. What is being redistributed is the fiber channel name server database, so the FCNS database. Here what I see is that exact same disk that I have connected on switch 1. So again, I show you here that the FCNS database is being transmitted between all the switches in the fabric. If I do a show FC domain, I see that this switch is not the principal switch. It's called the subordinated switch, which means DR other. So just another switch, not the principal. Question, is FCNS distributed by CFS? No, CFS is the Cisco Fabric Services protocol, and that is used to transmit information between fiber channel switches. That is correct. But all these things that I show you here, the zoning, the FC domains, the FCNS database, the principal switch selection, that is not a Cisco protocol, right? And CFS is a Cisco protocol. So it's just within the fiber channel protocol stack that this exists. So the fiber channel protocol stack exists of multiple standards, a lot of different standards, all describing those protocols. And Cisco has their own services protocol that they use to transmit information like NTP servers, like radius servers, and distribute that information throughout the MDS fabric. But that's only Cisco specific. This is for any vendor switch. This works the same on any vendor fiber channel switch. So like I said, this switch is not the principal switch, it's a subordinated switch. So in my case, it's running 104 as a domain ID while it had 00 configured. And you see that it got a different domain ID than the other switch. And that was assigned by the principal switch, because I see here, what is my local switch WWN? And what is the running fabric name? And the running fabric name means the switch worldwide name of the principal switch. Correct. We have another domain ID on this switch. 185 on one and 104 on the other. I can even see that if I do a show FC domain list, I see exactly what are the switches in my network. So I see the switch worldwide name. I see that I'm currently logged into that, and that it is the principal switch. And I see exactly what is the domain ID of that switch. Same happens for the other switch, 104. That is my other switch. If I do that same command here, show FC domain list, I'm currently logged into this one. So this is domain ID 104. And the principal switch is domain ID 185. And again, floggy database only for the local switch. So this other switch does not see that. Let's bring up the other JBOD connection. Switchport mode FL, no shut. So now I brought up the last connection here. This connection 5 is now also brought up. So I showed you here that I do not see any floggies until I open up a local port. And now I see here, I see 2 disks here. So 2 floggies are done. So there are 2 disks in this array. They have the same domain ID, the same area code, just different port ID. So this means that it's connected to some kind of a loop setup. They're both connected to the same interface. So how many entries do I expect to see in my fiber channel name server database? I see 3. And I see that one disk has a domain ID of B9, which is that 185. and I see that 2 disks have a domain ID of 68. So those are my 104 domain ID switches or devices. As soon as I check the fiber channel name server database on MDS1, I see exactly the same thing. I see 3 entries in the database and I see 3 entries here. So replicated to each other. And again, Floggy database only showing 2. What if I want to check my routing table? Show FC route. If I do a show FC route unicast, I see all my unicast routes. I do it from MDS2. So again, this is domain ID 185. This is domain ID 104. I'm currently on 104. So this translates to B9 and this translates to 68. So on MDS2, I do a show FC route. What I see is I see an FSPF route being learned for domain ID B9. That's correct, right? I should learn the B9 domain ID here on MDS2. And there is a concept of subnet masks, but only for a routing perspective. So I route only because of that domain ID. That's what it says here. And it has a cost value, so I can influence the routing protocol costs and make a whole topology about that. So very cool stuff. Do you have any questions about this? About this short demo that I give you, how the routing works, how the domain IDs work, how the worldwide names relate to the FCIDs, how FCIDs are assigned, how principal switches are elected, all that stuff. Question, can I explain about flags? Unfortunately, I do not know what the flags mean. I never looked at this before. I only take a look at this. So check your the configuration guide for this. So we have another question. The limitation of having 239 switches in the fabric is due to hardware or software. And how about interoperability between Cisco and non-Cisco devices? So that limitation, like I said, it's a 1 byte address. So that domain ID is a 1 byte address, meaning I can have a value of 00 up to FF, meaning in decimal that's 0 up to 255. Right? Now there are some reserved addresses. So the highest number I can use is 239, or actually 240, I think. A valid range of a domain ID is 1 up to 240. So this is a valid range of domain IDs. Domain ID 0 is not valid, and anything higher than 240 is also not valid. This is a software limitation. So this is how the standard defined how much domain IDs do I have. So I can have a maximum of 239 switches in my network. Now there's also, or this is a hardware limit actually, sorry, this is a more hardware related limit. Because it's hardware based because the standard defined it. Now, like I said, every switch in a network needs to have a domain ID. So if I have a lot of these switches with a lot of links in between, I need to communicate the FCNS database, the zoning database, running the routing protocol. So I ask a lot of the CPUs in the switches to run all those protocols. So you will see, depending on the switch that you buy, of course, and depending on all the switches that you buy, there is just a software limit that the CPU just can handle. That limit, depending on the switches again, is somewhere between 40 and 50 switches. So I can only have up to 40 or 50 switches in any given fiber channel network. There are tricks to work around that and go above this number. So 40-50 switches is about the limit on software. The hardware-based limit based on the numbers that you can assign is this, because of those reserved domain IDs. So we have another question. Is there anything like show CDP neighbors like on the Cisco devices? Not really, no. The best way to check your neighbors is with the show FC domain list. That's the best way to check for that. There is no such thing as show CDP neighbors. There is, but I will see it only on my management port here. There is a way though, there is one way that we can transport an IP packet into a fiber channel frame. This standard is called IPFC, IP over fiber channel. I can run, let's say, SVIs there to run to transport IP communication, and of course the IP connection runs CDP. But there is no such thing as CDP in the fiber channel world. So the FC domain list is the best way to check, do I have all my switches in my network and who is there in my network. And the comment about the trick that I said for scalability, yes, that's NPV. So the trick to go above this number is NPV. And that basically replaces my access layer technology. So my access switches will run in a bit of a different topology than a normal fiber channel switch would do. Question, is there any way of easily telling what ports connect to other switches? Unfortunately not. You can do a show interface brief, then I can see exactly what are my E ports, but what is exactly connected behind that, I cannot see that here. There's no communication about that. So the domain list shows you exactly what devices are behind you. With my FC route command, I can then see what is connected directly behind me based on cost and based on number of hops. So then I can basically start making a diagram, but there's no way of telling, is MDS1 connected to me or MDS3? I cannot tell that from the CLI. Any other questions? You're welcome. Thank you. So we have a question, is control plane traffic sent down a separate channel on the same physical port between connected switches? No, it's just similar to how that works in the Ethernet world. So I send my span tree BPDUs in the same channel as my normal Ethernet traffic, and the same on routing stuff. So there's no separation in control plane traffic or data plane traffic. It all runs across the same wire in the same channel in terms of forwarding. I do use different FCIDs for that. So I have a special range of FCID addresses for let's say multicast and broadcast traffic. So same concept of Ethernet, and that is used for exchanging control plane information, just like I do on the IP world. All right, thanks, Dominic. So we have a comment that there was a lecture about MDS security that has been cancelled. That will probably be moved to January. So we had that scheduled for last week, which was Thanksgiving, which was not a very a good schedule, of course. So that's why we moved this, and we had some requests for doing the fiber channel lecture first. So there was a comment from some people saying we want to know more a little bit about the basics of fiber channels. So that's why we took that subject and changed that to this, and we might do that somewhere in January. Exactly, something about turkeys last week. So question, can I share the recording of this session? Definitely. Like I said, it's going to be published on YouTube on our IP Expert Inc. YouTube channel. So just monitor that or monitor our blog. We'll be definitely posting it there, and you'll be freely watch it there anytime you want. So all our free lectures on all of the CCIE tracks are shown there. So you can see them there. By the way, if you have any questions, we have an online study list for the CCIE Data Center. Should you have any technical questions, please ask them there. Sign up for that mailing list so you get all the emails and stuff. And I'd like to thank you for your time. Thank you for your trust in IP Expert. And I hope to see you soon in one of our CCIE Data Center boot camps, or any of the other boot camps, of course, for any of the other tracks. So this was the last V lecture for this year, maybe. We will, of course, continue with this in January, and I hope to see you then, or I will see you in a class sometime. So thank you very much for attending. Thank you for all your questions. Thank you for making this very interactive, and I hope to see you soon. So if you have a question, how do we register for the CCIE Data Center list? Go to onlinestudylist.com. So this onlinestudylist.com, onlinestudylist.com, go there. There you can register for the list, and then you will get all the emails and can start replying to that. And we have a question, do we have any spots left in upcoming DC boot camps? I think the next 2 classes are already fully booked. Of course, always check with sales. So sales@ipexpert.com if you have any seats available. So next week we will run an online class like in this classroom. And in January we're going to do a live class in San Jose, but I believe they're already fully booked. So there are more boot camps scheduled, but there might be 1 or 2 seats left. So please check that with sales. So again, thank you for attending. I'd like to close down this now. And if you have any questions, please email me on rmur@ipexpert.com. So I hope to see you soon, either live or in an online class or in any of our classes. So thank you. Please do a thumbs up if you liked it, and then I'll see you soon. Thank you. Bye-bye.